Okay, we're on to the short answer paragraphs from Unit 5. And you probably recognize this from this setup from an earlier question, but they're going to ask it a little bit differently. So we've got our launcher used to launch a dart with initial speed v from a table at an angle as shown. The dart exits the end of the launcher at a height h above the floor and lands a horizontal distance d from the end of the launcher. Close-up view is included. Inside the launcher, the dart rests on a platform with negligible friction, and a compressed spring is released to push out the dart out of the launcher. Assume air resistance is negligible. So part A, we're going to analyze this free body diagram. Again, you won't have to draw one, but I'm sure you'll have to analyze one. A student creates the incorrect diagram shown above of the forces exerted on the dart an instant in time after it's been launched, but before it reaches the floor. Indicate what aspect of the diagram is incorrect. Assume air resistance is negligible. So we touched on this last time we hit this setup. Once the spring is released and the dart is launched, the dart is in free fall. So the free body diagram should just be gravity, like this, which in our diagram is pretty clearly F sub earth. There is no F sub dart. I can't imagine, that's not the launching force. It's not the force on the dart. It's not the force exerted by the dart, since this is a free body diagram of the dart. So the incorrect part there is that the horizontal force is wrong. Or you could have said F dart needs to be removed. However you slice that. That's part A, 1.4 part A. So part B, the student produces the three possibly incorrect graphs, which show the representing properties of the motion of the dart after it is launched. So again, this is at heart a projectile problem. And do you know how projectile motion works? So the brief recap there is that the horizontal velocity is constant throughout the trip. The vertical velocity, the speed down decreases. So if your velocity, if up is positive, then your acceleration is negative. And so the slope of your vertical velocity versus time graph is negative. Acceleration is constant at 9.8 meters per second squared down. So that's just a recap. Part B says, another student claims that the horizontal velocity graph is not correct because the dart is accelerating and therefore the horizontal velocity is not constant. Is the student's claim valid? Well, the dart is accelerating. That part's correct. However, it's not accelerating in the horizontal direction. It's only accelerating in the vertical direction. So it's okay that the horizontal velocity graph is constant. So you get a point for saying that the part about the horizontal velocity being not correct is invalid. You get a point for that and attempting to explain it. 1 point for explaining that the acceleration is vertical, or you could say the acceleration is not in the horizontal direction, however you slice it, to say that the horizontal velocity doesn't change. So 2 points for part B. Now we're on to the paragraph, okay? That's not a very good C. Now we're on to the paragraph. So what's it going to say? From the instant the dart is launched until it reaches the highest point in its trajectory, the magnitude of the dart's velocity decreases. Okay, and that's true. In a clear, coherent, paragraph-like response, explain the following. Why the magnitude of the dart's velocity decreases until the dart reaches its highest point, and why the magnitude of the dart's velocity does not decrease to zero. So the gist of this is that you've got to address the fact that the velocity is the vector sum of the components, so that at any point, right, the square of the magnitude of the velocity is equal to this. Now, you don't necessarily have to say this, but you do have to touch on the fact that the velocity, the magnitude of the velocity, depends on the x component and the y component, right? So Vx remains constant, Vy decreases. Okay, remember, we're just talking about to the top of the loop, to the top of the trajectory here, yeah? Vx is chugging along, Vy decreases, eventually becomes zero, all right? So for that reason, since Vx remains constant and Vy decreases, the magnitude of the velocity decreases. Okay. Why does it never become zero? Well, because Vx is never zero. So even at the top of the trajectory here, when Vy is zero, Vx is still V sine theta, whatever it was when it started going. So those are the points you need to hit for the paragraph. 1 point for indicating that velocity has two components, the vertical and the horizontal. 1 point for indicating that Vx remains constant while Vy decreases. Again, this is only the on the way up portion. 1 point for saying that the resultant velocity decreases because the resultant velocity is the vector sum of Vx and Vy, so something like this. 1 point for saying that V cannot be zero because Vx is never zero. And then 1 point for the logical paragraph. So that was really, what do you know about projectile motion, which is a good question there. Now you're probably wondering, why is this a Unit 5 question? Because that was all Unit 1 stuff. Well, Part D, I guess, is the Unit 5 part. We were just on a roll, and now we're going to do this stupid thing again. The dart is now launched so that it collides and sticks to a wheel at time t1, which is the instant the dart's velocity is completely horizontal, as shown. The wheel's initially at rest, and it's free to rotate about a pivot at its center that has negligible friction. A short time later, at a time t2, the dart wheel system is still rotating in a counterclockwise direction. At time t2 is the angular speed of the dart wheel system about the pivot point, increasing, decreasing, or constant. So this is I guess it's really the Unit 5, sort of the Unit 6 question. So what's happening? Basically, the angular velocity is going to be decreasing at that point, okay? The angular velocity is going to be as fast as it's going to ever be when that dart hits, because as the wheel starts to spin, gravity is going to exert a torque on that wheel and slow it down. So 1 point for saying that angular velocity is decreasing and an attempt at an explanation. All right. And then 1 point for the explanation being correct, which is basically that there's a net torque exerted by gravity that's opposite to the direction of the rotation. Okay. If the dart hit at the top and started it rotating clockwise, then it would be speeding up, right? After a little while, because gravity would help that. But in this case, it's starting it to spin counterclockwise. Gravity's going to oppose that. So 2 points there for Part D. So again, even if you had no idea what to do with that dart and the wheel and all that stuff, you could have gotten the bulk of those points from a good conversation on projectile motion. So that's our first one from assignment 11.